All right, welcome back everybody. We are continuing to talk about our variability module by connecting those measures of variability to some aspects of distributions and populations that we've talked about as well. This is a really important lecture because it has a lot to do with how we use variability again towards that process of finding statistical significance, how we use it to learn about those populations that we generally care about. So, let's see some of how this works. So we have our measures of variability, our variance, and our standard deviation. The standard deviation is the one we're generally going to be using from here on out. One of the assets of a standard deviation is because it's a standardized formula, it can be used to clearly identify where a score falls on a normal distribution. What I mean is this. You can take any score on any variable that follows a normal distribution and you can represent it in terms of how many standard deviations from average it is. If it, of course, is exactly on average, it's 0 standard deviations away, it's exactly the same as the average. It could be 1 standard deviation above, 2 standard deviations above, 3 above, and the same for being below average. So again, we can represent scores in terms of how many standard deviations away from the mean they are. Are they above or below average? And how many standard deviations is that deviation? Either way, notice that the farther away you get from the mean, the lower the curve gets, which means scores are more and more infrequent. So the more standard deviations away from the mean your score is, it also becomes more improbable. It becomes less common. So we can see here some rough estimates of, again, what percentage of a normal curve is between different numbers of standard deviations. So again, no matter what the original variable is, no matter what the original scores look like, if it follows a normal curve in the population, we know that about 68%, just over 2 and 3 scores, are within 1 standard deviation from the mean. 34% between the mean and 1 standard deviation below, another 34% between the mean and 1 standard deviation above. Then we look here and we see another about 14% on each side is between 1 and 2 standard deviations from the mean. We add those up, about 95% of scores in a population that follows a normal curve are within 2 standard deviations of average, and over 99% are within 3 standard deviations. Very, very few people in an entire population are more than 3 standard deviations away from average in either direction. So the farther away you get, the more unlikely those scores become. The vast majority of scores are within just a few standard deviations of the mean. So this is for future service. Again, everything with the normal curve, your ears should perk up. That's stuff that's really important. The standard deviation gives us this ability to standardize how we represent our scores, or we can represent them, again, in terms of how many standard deviations above or below average it is. This is a measure of what's called relative standing. It tells us where scores fall relative to the rest of the population. If I know how many standard deviations away from the mean it is because of the way the normal curve works, I can make very precise estimates of what percentage of the entire population is above or below that score, or between any 2 scores. Again, I can do this because of the standardization, the precision of that normal distribution. So this gives us a level playing field. Can't overstate how important this is. Distributions from variables with totally different means and standard deviations that are measured in totally different ways, as long as they follow a normal curve at the population level, which is a pretty safe assumption as we'll find out later, we can now compare them using that normal curve and using those standard deviations to measure what's called relative standing. More of this to come immediately after the next exam when we talk about z-scores in the next unit. So remember, with the mean, we said, okay, we calculate the sample mean, but what we really care about is the population mean. It's the same for the variance and the standard deviation. Both of the formulas you've seen, the s squared and the s, those are sample statistics. Those represent data we get from samples. They aren't the characteristics of parameters. The population variance, if we wanted to calculate it for the entire population, notice our s now changes to a lowercase sigma. And notice here in the formula, our mu changes to, or excuse me, our m, our sample mean, changes to a population mean, because we're now dealing with populations. But otherwise, this is exactly the same as the original definitional formula. We have a symbol that reflects that this is the variance for a population, that's sigma. We have a symbol that reflects that we're dealing with a population mean, mu. Population standard deviation, you just take the square root of that result. But here's the thing, I'm going to backtrack for a second. Here's the thing, these formulas aren't that important because in practice we never have every score in a population. That's what we need to actually run these. Here's what is important. Both the sample variance and the sample standard deviation are just ways of estimating these parameters. We would really love to know these parameters because they describe every single person we're interested in, those massive populations. We use that sample data, again, to try to estimate that. So, just like the population mean, we generally can't know parameters. We'll talk about some cases where we do know those, but those are really specific situations. They're pretty uncommon. So usually we never, ever are going to know what these parameters are. So here's one extra wrinkle with the variance and the standard deviation. Remember we said if you don't know what mu is, if you don't know the population mean, your best estimate is the sample mean. Okay? In the case of sigma and sigma squared, our population, standard deviation, and variance, the sample statistic actually doesn't give us the best estimate that's possible. The reason why, those sample statistics are what are called biased estimators. They are going to consistently give us estimates of the parameters of the population, standard deviation, and variance that will be too low. Here's the reason why, essentially. Again, the farther away you get from the mean of a normal curve, the more and more infrequent the scores become. They become less and less common. So at the extreme, you have scores that are going to happen 1 in a million times, 1 in a billion times, 1 in a trillion times. It's really, really, really unlikely that those scores will wind up in an average size sample. So those scores get factored into the population variance, those extreme outliers, but it would be extraordinarily unlikely that they're going to show up in your sample. Think of like a person with extraordinarily high intelligence or extraordinarily low intelligence. They're very unlikely that one of those people, those extreme cases, are going to show up in your sample. So your variance will be a little bit lower than at the population level because those extreme outliers aren't showing up in your sample. Long story short, we want to get rid of that bias. We want to make it so that it's still an imperfect estimate of the parameter, but that the errors are what are called evenly distributed. It's equally likely to overestimate and underestimate it. That makes it an unbiased estimator. Still imperfect, just equally likely to err in either direction. So, again, fortunately for us, the actual mechanical changes are very easy. If you've read the book, which you should have, you'll notice that they talk a lot about this formula that looks like the one we've learned already, but instead of n in the denominator, it's n minus 1. This is the most commonly used formula for variance. The reason why, we make the denominator a little bit smaller. That makes the result a little bit bigger. If you divide 20 by 5, you get 4. If you do n minus 1, subtract 1 from the denominator, 20 divided by 4 is 5. You get a bigger number. So the denominator gets a little smaller, the variance gets a little bit bigger. That makes it more of an unbiased estimate, where it now is equally likely to overestimate and underestimate those population parameters. So it's still not perfect, but it's unbiased. It's still going to have some inaccuracy, but those inaccuracies are going to be what's called evenly distributed. They're going to be spread out equally instead of all going in one direction. We're going to use this new formula for the remainder of the course, that n minus 1. That's the version you'll see on your quizzes. That's the version you'll see on the exam that's going to come up very shortly. So before we get to that, our point of emphasis, number 2, is again using variability to estimate those parameters. So to recap what we just talked about, we can calculate sample statistics, but what we really want to know are these parameters. The problem is that these statistics are biased estimators. They tend to underestimate the real parameters. So we make this adjustment. It's still imperfect, but it makes them, again, more unbiased. Those errors, those mistakes, the inaccuracies in the estimation are equally likely to be overestimating and underestimating the actual parameters. Just like with means, when in doubt, get more scores. When we measure more people, the standard deviation and variance become more and more accurate estimates of those population parameters. And keep your eye on this distribution map here and this idea of z-scores. This is going to be a really important foundation to what we're going to talk about in the next module. So that is the end of this lecture. It's also the end of this unit. So at this point, you should be in full test preparation mode. Hopefully it's not coming up in just an hour or two, but you will need to kind of stop here. You can look ahead if you want, but you can only take the exam on the date listed on the syllabus. So again, review the instructions for taking those exams if you want. Test your equipment. Definitely review practice problems. Make sure you're caught up on homeworks, etc. And best of luck on that exam. When you're ready, whether that's before the exam or afterwards, start the next unit by opening the next module on z-scores, and we'll start putting together that puzzle of hypothesis testing. All right, I will see you probably on the other side of that exam. Good luck to everyone.